Okay, hello boys and girls. Welcome to our fourth lecture here, the lecture on limits. So today we do introduction to limits. Now you should understand that today we're not doing all of the limits. Limits is a huge topic. In fact, it's going to take us a few weeks here to get a little taste of them. So I think it's way too much to do in one lecture. Way too much to do in one day. We're going to take little tiny baby steps. So today we just do the introduction. We try to get our heads wrapped around the idea of what it is that a limit represents, and we try to maybe establish two different methods for finding limits, and we try to find maybe 5, 10, or 15 examples of limits. If we can get that done today, we will call it a success. Okay. Just introduce the idea, calculate several of them using two different methods. That's it. Very modest goals, baby steps. They say a journey of 10,000 miles begins with one single step. Think about that. Anyways, limits, what they are, they're really just one powerful way to think about them is they are best predictions of a certain type of event that's going to happen. In a nutshell, that's probably the deepest you can get with just one sentence, with just a few words. They're best predictions. Okay? And for us, it will be the perfect medicine for all the vices of the previous idea. The previous idea was this idea that we've got to dominate arithmetic using these indeterminate forms. And for us, limits represent the perfect medicine for those indeterminate forms, like you put in intermediate, they're indeterminate forms. So let's take a look. What do they look like? Well, limits look like this. They have the syntax is this. They have they say lim, which represents limit, and we usually say limit of whatever's in here as something happens. So two things happening. This is what we're going to be trying to do is we're going to be trying to predict where this is headed, whatever's in here. This might change as something else changes here. As this change occurs, this changes here will occur here, and we're trying to do is predict exactly what's going to happen here as this thing changes. I know it's a lot, but I've got a perfect example to illustrate the syntax. This example is just illustrating the syntax. It's not explaining anything else than, well, it's actually explaining a lot, but just roll with me. So I don't know if you guys could tell what that is, but that would be a cocoon. I know I'm going to get thousands of letters, but the correct biological term, whatever. That's a cocoon, which means it's where the butterflies start off being. It's a monarch butterfly inside. So the limit would be, I'm trying to predict the cocoon here. What's going to happen? What's the best prediction for the cocoon? But the syntax is not complete. As what? As as time goes off to infinity, as time goes off to the time of dinosaurs. What? We need another part of the syntax. This would make it more clear. This would say, what's the limit of this cocoon? What's happening to this cocoon as the date approaches spring? So the date is changing, and it's going to approach spring, and I'm trying to find the best prediction. What is the best prediction for this concept as this happens, as the date approaches spring? Now, as many of you biologists know out there, most of these monarch cocoons hatch in the spring. So what do you think the best prediction is as time approaches spring? Of course, the best prediction would be that the cocoon will turn into a butterfly. It doesn't mean that it did. It just means that that's the best prediction. It's really important to understand that carefully and make that distinction. Maybe it turned into a butterfly, maybe it fell off and died, maybe a bear came and ate it. I don't know. We don't know. The limit is not concerned about what actually happened. The limit is most concerned is what is the best prediction? What does this seem to be approaching? For all we know, maybe the Earth ceased to exist before spring came along. Well, that's a dark view, but whatever. The point is that this is only the best prediction of the cocoon. If all things go as planned, as the date approaches spring, it would be a nice monarch butterfly. That, my friends, that's the syntax for limits. Now let's try it on an actual problem from our class. This is what an actual problem would look like in our class. You're trying to find the limit of this creature here, 5 over x, as x moves closer and closer and closer to infinity. Got it? So this is the way we read it. Limit of 5 over x as x goes towards infinity. Now, I said today we got the two important approaches. Let's try the first one first. The first one is the most primitive of all approaches. It involves something called that I called engineer's method, and nobody else calls it that. I just think it's very descriptive to call it engineer's method, and so I have. Engineer's method says, you know what? If I want to see what happens to this as x goes towards infinity, one approach is just to actually try numbers that seem to be approaching infinity, and then try to make the best prediction for this quantity. Clear? You'll see. So one way to do it is to make a little chart here and say, alright, I'm going to make a chart, and I'm going to have two things happening here, the x values and the expression. The x values, I want the x values to be going towards infinity. See, this goes to 100, then it goes to 1,000, then it goes to 100,000, then it goes to 10 million. My x values are going towards infinity. Okay? And as x moves towards infinity, I want to know the best prediction of 5 over x. So at 100, I want to take a picture here, divide 5 divided by 100. You would do that on a calculator, just go, 5 divided by 100, and you would put that here and make a note of it. And then you would do the same thing, 5 divided by 1,000, and put it here, 5 divided by 100,000. And then you would want to know what is the best prediction as x goes towards infinity, as x moves towards infinity, what is the expression doing? If we can find the best prediction for that, we will have successfully found our first limit using what I call the engineer's method, more or less. So I worked out this problem, and I found out the values here. The values are, for when x is 100, your expression is 5 hundredths. When x is 1,000, you got 5 thousandths, and so on and so forth. Now, as x is moving towards, rapidly moving towards infinity, we've got to make a prediction here. What is the expression moving towards? Dun, 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 dun. This expression is getting closer and closer and closer, and it might get there, it might not, but well, it depends if you go all the way to infinity or not, but it seems to be getting closer and closer and closer to one famous bucket. It's getting closer and closer and closer to, of course, the zero bucket. So we will call this limit 0. The best prediction is 0. And so we say, okay, this limit is equal to 0. And there, you're done with your first limit. Okay, using the engineer's method. That wasn't too bad, right? Let's try again another example. So here's our second example. Suppose you wanted to find the best prediction for this quantity here. Quantity 3 plus 1 over x as x moves towards negative infinity this time. So we're trying to find the best prediction of this. What is the best prediction? Best prediction. Oh, this thing is cute. It does that all the time. So anyways, note here my x values. My x values, I start off with negative 100, then I went to negative 1,000, negative 500,000, whatever. I just wanted to vary it up a little bit, so you see there's nothing special about the other ones I chose before. Really, these numbers could be anything, and it shouldn't be depending on which ones you choose. As long as your x's are going towards negative infinity, we want to observe what's happening here. What is the expression doing, and what is the best prediction at the end? That's the name of the game. So you pick some numbers. This is the engineer's method. It's the most primitive approach to limits, and it's a good way to start. So I did some computations here. So we can pull these up. Come on. There they are. So I did some computations, and then I got 2.999 here, 2.99, 2.9999999, 2.9999. As your x's move towards negative infinity, what do you suppose the best prediction would be based on these values of the expression? What do you suppose would be your best prediction for the expression? If you said 3, then we've got something good going on here. That would be the best prediction as your x's move towards negative infinity. See? Easy. Here's another way to do it. I said only 2 methods, but here's the beginning of a third method. If you could somehow plot the equation, this is let me see, I'll do it on red. This is y is equal to 3 plus 1 over x. This is the graph of it. And you see, as your x's are going left and left and left, these are your x values. What is you look at the red graph. I'm going to put my finger on it. My fingers are going left towards negative infinity. What is the y value doing? The y value is the expression. The y value is becoming incredibly close to this horizontal asymptote at 1, 2, 3. This is the line y equals 3. And as x goes towards negative infinity, my y value gets closer and closer and closer to 3. So you just put your finger like this, and as x's move that way, you're trying to ask what is the y doing, and the y's value getting closer and closer to 3. We will actually make a method out of this. This will be called the graphing method in the next couple sections. But perhaps it's instructive to show a first glance at it here. I'm sure to make it really familiar. This is what a limit is. It's the best prediction of the expression as x's move, roughly speaking. Anyways, here's another. I told you two methods. Here's a second way to approach it. This is what I call the plug-in method. It doesn't always work, but when it does, it's kind of nice. So suppose you go on and you say, you know what if I just went in, so since x is going to go towards infinity, why don't I just go ahead and plug in infinity there and see what happens? If you think that way, you'll get, well, this is 5 over infinity. And every once in a while, when you do that, you can actually resolve it. This is the type of arithmetic that we can do. You just have to think 5 divided by a large number. Well, that becomes a really small number. That becomes in the 0 bucket. And so you're done. You're really done. See how easy that is? That's called the plug-in method. I usually like to put on here plug-in method to indicate that it's not really equal. It's pseudo-equal maybe if the plug-in method succeeds, which it does sometimes. Okay. Also here, so I'll do plug-in method. By plug-in method, this would be 3 plus 1 over infinity. And you say, well, what in the world is that? Well, 1 divided by infinity, that would be 1 divided by a huge number. That's in the 0 bucket. And something in the 3 bucket plus something in the 0 bucket, well, undoubtedly that's something in the 3 bucket. And so there it is. The plug-in method succeeded here. All you do is plug it in. On a good day, not always, but on a good day, the plug-in method is good enough and you're done. And you may be wondering, well, then why in the world do we bother with this kind of stuff, the engineer's method? Well, I know, here, try the plug-in method again. The plug-in method, plug-in it would be 31 plus infinity to the third. Then you have to think, is that something that we can do? Infinity times infinity times infinity. Do we know for sure what that is? If I pick something from the large number bucket and multiply it times something else from this large bucket number, and then multiply it again by something else from the large bucket number, will I get something that I know for sure what it is? And the answer is, to some degree, yes. We know you'll get something really large. It'll be in the large bucket, and so then you add 31, and of course you get infinity. So it's completely determined. This limits. Whoa. I was just trying to test you guys to make sure that you're paying attention. It is incredibly important that you pay attention to see where the x is going. I had assumed it was going to positive infinity, but it's not. That's how you would do it if it was going to positive infinity. And I'm going to leave that there. I won't edit it out because I think it's instructive. Let's do it again. Now this time x goes towards negative infinity. So this would be 31 plus negative 31 plus negative infinity raised to the third power. So that would be 31 plus, let me think, negative infinity times negative infinity times negative infinity. These two negative infinities would give you a large negative number times a large negative number would give you a positive large number. For sure, there's no doubt, independent of which one you pick from the basket. Large negative times large negative gives you a large positive. Moreover, a large positive times a large negative gives you a very, very large negative number. And then you take a large negative number and you add positive 31 to it. There's no doubt the 31 will do almost nothing to it. Yeah, the negative infinity will laugh at the 31. Of course, and swallow it up like there's no tomorrow. And so this is conclusive. I should have put here the plug-in method. The plug-in method succeeds here very, very nicely. All you do is calculate using common sense, our notion of buckets, and some common sense, and that gets you a lot of times on a good day to get you to the answer with not a lot of obstacles. And again, that should bring up the next question. Well, why in the world do we bother with the engineer's method? Let's try to see if the plug-in method works here. If you try the plug-in method, that would give you 3 times, I'm checking now where x is going. This is really, really important. You can't ignore that, as I brilliantly showed in the last example. So this is the plug-in method, and then you try to work through it and see if everything can be worked out carefully and correctly and conclusively. Infinity times infinity, there's no doubt in my mind that's infinity. 5 times infinity, there's no doubt that's infinity. 3 times infinity, there's no doubt that's infinity. Infinity plus infinity, I got that, that's infinity. Infinity plus 2, that's infinity. No doubt this limit is clearly going towards infinity. Well, if you can see that, there you go, you can see it now. Plug-in method, very, very nice, right? So then why do we do the other one? Let's try it again, plug-in method. The plug-in method again, so x is going towards infinity, as we are supposed to observe here. And now I have to try to predict this expression. So I try the plug-in method, plug in infinity there, times sine of 1 over infinity. And then I try to see if I can figure that out conclusively and without any paradoxes. So sine, let me think. I can figure this piece for sure. This piece, little piece, focus all your might and all your attention here. 1 over infinity is conclusively 0. 1 over a huge, huge, huge number, that will give you something in the 0 bucket. And then, what is sine of a really, really small number? Sine of 0, well, that's, everybody knows, you took an excellent trig course, sine of 0, 0. And then, whoa, penalty. Uh-oh, something bad happened here. Infinity times 0, that's an indeterminate form. I'm going to put it in red. Indeterminate. Indeterminate. This is one of the, you have a large, again, I don't want people to memorize it, I want you guys to understand. A large number which tries to make everything large, multiplied times a small number which tries to make everything small. You put them together and all bets are off. It's opposing forces, and who knows who would win. So that is why the plug-in method, this exposes exactly the problem with the plug-in method is that a lot of times it doesn't work. It gives you things that are outside of the scope of things we can calculate. It gives you indeterminate forms. And so at that point you say to yourself, you know what, the plug-in method failed because it gave me an indeterminate form. So then you see the purpose of previous part of the lecture. That is why we started with the engineer's method. Often when the plug-in method fails, this is something you can always go back to, the engineer's method, to try to give you a good guess of what the answer is. And so then you go back to your table here, and your axis is traveling towards infinity, so you pick values that are large, 100, 900, 2000, 52,000, etc. And then you try to compute the expression. I did this on an Excel sheet, something like on a spreadsheet. And I computed it, and see, you can compute those, any calculator will do, or Excel, whatever you like. This is really, really good to get an intuitive idea of what limits are. I told you it's not the whole limit story. We've got to take it easy. That's like a 2 or 3 week story, but this is a good place to start with the engineer's method and the plug-in method. So I put these in on the spreadsheet, and here's what I got. I got 0.999983 when x is 100. Then I got 1. My spreadsheet was running off too, by the way. I don't know, about 7 or 8 places. So this means maybe not completely 1, but maybe it was 1 with a bunch of zeros and maybe some stuff afterwards. Another 1, and then you get 0.99999. So this is a little, it should make you a little bit afraid. Whoa, what's happening here? Some of you may want to say, well, this is, let me think. Some of you may want to analyze it this way. As your x's go bigger, 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 and bigger towards infinity, oh, your y's are going towards 1. See, subconsciously I'm doing the graphing method here. Your expression is going towards 0.99, 1, but it went down again. It doesn't seem to be going up consistently. Then it goes back up. It's a little risky, but if you're bold, if you've got guts, your best guess might be something like 1. The best prediction where this is headed towards is 1. That should make you feel a little bit good, a little bit uneasy, because this kind of worries me. The fact that it's not really going towards 1 in a straight path. It seems to be oscillating, and and that's okay. I want you guys to be uncomfortable a little bit. It will be part of the lecture later. We'll come back to this idea. For now, though, let's just roll with it. The best prediction seems to be 1. Maybe we can just classify it. That seems to be the best guess. This is an important comment to make here. Best guess based on the engineer's method. Okay? Nice. By the way, this is super famous. Ridiculously famous. Okay? I don't do nothing but the famous stuff. No, not really. Sometimes I do unfamous things. Well, but anyways, let me come back to this point. Why in the world were we doing the engineer's method? Because plug-in method often fails. It gives you indeterminate forms. So when that happens, you can always fall back on the engineer's method. Okay, try this one. So you try the plug-in method. Are you guys afraid or not? Let's try the plug-in method. If I try the plug-in method, everywhere I see x, I plug in infinity. So I'll give you infinity minus the square root of infinity minus the square root of infinity squared plus 5 infinity plus 21. Now I want to take really careful steps as to not to do things that I don't know for sure. I'll handle this piece. I know this one for sure. If I have infinity raised to the second power, that means a large number times a large number. It's not very controversial. I think everybody can agree that the result would be a large number. Same thing with this. If you have 5 times a huge number, well, that's going to be a huge number. That part is not controversial. Infinity plus 21, that part is not controversial. If I take the square root of an unbounded number, I will get an unbounded number. What do you get here? The best that the plug-in method can deliver for us is that we've got an indeterminate form. Well, so much for that, right? So much for the plug-in method on this problem. On this problem, because it gave us an indeterminate form, you can declare it failed. You're fired. We got to come back to the only other method we know. So far we know 2 methods, the engineer's method. And so we make a little chart here. We observe our x's here. Our x's are going towards infinity, towards infinity, towards infinity, towards infinity, towards infinity, and we're trying to make predictions on the expression. What is the expression going towards? And so again, you can use a calculator for now. Calculator is fine. You can do it by hand if you like. Maybe if you're watching this from an incarcerated place and you got nothing to do, you could do it by hand. I'm just kidding. If you got no life, you got no friends, you can do it by hand. Anyways, if you've got a spreadsheet, you can try a spreadsheet on this, like I did. And I observe. Let me cover these things here. I observe when x was 100. The expression turned out to be negative 2.5719 whatever. When I moved it up to 980, it's still negative 2.58. It's a little smaller than the previous one. This one's a little smaller, but still bigger than 2.5. This one's a little smaller, still bigger than 2.5. You see? If you had to guess, if somebody put a gun to your head, no, if somebody put a chocolate in front of you and they told you, if you guess, see, positive reinforcement is better. If you had to guess, as x's move towards infinity, what is your y doing? What is the expression doing? If you had to guess, if you guess 7, I'm out of here. I'm going to call this quits. No, you can't be guessing 7. Your best guess should be, based on the table here, your best guess should be negative 2.5. Right? Based on the engineer's method. Does that prove it? No. Is it the best guess? Yes. Based on the engineer's method. That's what it is. Okay? Try another one. Plug-in method. If you try the plug-in method on this guy, infinity over the log of infinity. Now, what is the natural log of an unbounded number? One way to think about it is e raised to what power gives you an unbounded number? Well, you have to raise it to an unbounded number. Because if you raise it to a bounded number, you'll get a bounded result. So this is infinity, ln of infinity is infinity. Look what you got. What do you have here? Indeterminate form. Indeterminate form. By the time you get an indeterminate form, you should be thinking, whoa, more work is needed. Violation. And so we go back to the only other method that we know besides the plug-in method, and that would be, of course, the engineer's method. So we declare the plug-in method failed here. Failed miserably because we get an indeterminate form and we set up for our... Whoa, what happened there? Notebook. Anyways, we tried the engineer's method on this one, and we observe the x's. We make a little chart here. X's are going towards infinity, and we try to observe exactly what are the y's doing. And let's look at the expression. First it was 21, the next was 142, 580, 10,000 and change, 72,000 and change. If you had to make a prediction, as your x's move towards infinity, what does your expression move towards? And you'd have to guess infinity. It goes into the infinity bucket. Seems to be growing indefinitely. That would be the best guess based on the engineer's method. Okay. Oh, this is a super famous one. Looks like it's done already. The plug-in method failed because when you do the plug-in method, you get 1 plus 1 over infinity raised to the infinity, which becomes 0, so that becomes 1 raised to infinity. And you know that 1 is right on the fence. Anything below 1 raised to infinity would go to 0. Anything above 1 raised to infinity would go to infinity. So this is an indeterminate form, a famous indeterminate form. So the plug-in method fails here, and we've got to go to the engineer's method. Again, this one is ridiculously famous, and it's really important. So you plug in different values: 2.69, 2713, 2715, 2717, 2718, 2718, 28. This is harder than the other ones, I think, because as this goes towards infinity, these numbers keep growing and growing and growing and growing and growing, and it forces you to ask the natural question: what if they keep on growing forever and ever and ever and ever? That's a very legitimate concern for any self-respecting human being. What if they keep on growing forever? And it exposes, at the same time of doing this timeless problem, it's exposing the problems with the engineer's method. You have to take wild risks when you call this, well, this is going to approximately 27, 18, 28. You're taking a huge risk because, you know, maybe we didn't go far enough. Maybe if we go to 200 million, it'll get past 3. Yeah, that's a legitimate concern. Exactly. So it exposes exactly the problem with the engineer's method. It's a guess, man. That's what engineers do. Oh, sorry, did I offend engineers? They just guess. Wah. The math hands guy offended me. Wah. That's right. A lot of times they just guess. Mathematicians love to prove things. There's nothing else that makes our muffler smoke more than a proof. A proof that is set good and it's good forever, and we know exactly for sure it's true. Other people, such as engineers, they are not so big on proofs. From what I gather, or just for fun, we're just making fun of them, whatever. That's why it's called the engineer's method. It's a guess, and that exactly is it's a guess, and that's the problem, that it's just a guess. I'm not saying we shouldn't do it. I'm just saying that there's some problems with it, and so we have to guess that it stops at about 27,828, which in fact it does. It stops at a not exactly that, but it stops at the incredibly famous super number called E, the natural number E. That's why this is super famous. The limit is exactly E. But this is such a good problem for various reasons. Okay, one, because it's a famous limit, and second, because it really plainly exposes the problems with the engineer's method. So I think that's pretty close to maybe more than 20 minutes. I think I got everything that I wanted to say out. I've written some homework for this, so you should try it. Really important to try the homework. And let's just finish up on a little summary of limits. We tried two different ideas, the plug-in method and the engineer's method. I want to just say a couple of words about the pros and cons. The plug-in method, the good thing is that it works so easily. It's fairly straightforward. I don't want to write easy, because I think easy is often overrated. I'm going to take both hands to write this. Easy. That's hard. But easy is overrated. I don't want people to think that whatever. I'm just gonna let that slide, okay? The bad thing is that it often does not work. It often fails, and you can qualify that even more. When does it fail? Well, for example, it fails when you get indeterminate forms. So, and that's a lot of times. So very often it fails. Specifically, for example, it fails when you get indeterminate forms. Engineer's method, on the other hand, the good thing about it is very intuitive. Very intuitive. It's good for beginners. Good for limit beginners. If you've never done limits in your life, this is a good way to start. It's very intuitive. You're just trying to predict a value, and you choose numbers that are really getting close to infinity. Very intuitive. It's just powerful. The bad thing, this is a huge bad thing. The bad thing is that it's just a guess, and often, almost always, you can never really be sure that you've got the right limit. All it is a guess. Now, if you're an engineer, hey, life is good. You're good to go. But if you're a mathematician, guesses are just not good enough. We love proofs. We love knowing things with certainty, perfection, beauty, and creativity and reasoning. That's what we sell. Anyways, I thought we could finish off today with just a different way of viewing this whole limits and indeterminate forms. Imagine a soccer game. Hopefully, soccer is international, man. Everybody plays soccer. Hopefully, you've played soccer. You know a little bit about it. Every time that the ball goes out of bounds, what happens? There's some special attention given to the track trajectory, specifically to the point where it exits these boundary lines, right? The special attention is given is that the ball has to come back, and you bring it inbound right at that spot. Right? So, for example, if the ball went out of bounds that way, special attention is given to this trajectory, because that spot right there, that's where the ball has to be placed when you bring it back in. So it's always this idea of observing, where does it get out? Where does it get out? Does it get out here, here? Where did the ball get out? Right? That right there, I think it's a powerful analogy to understand the connection between limits and indeterminate forms and the plug-in method, everything that we talked about today. Because you could think about the outside, people call it outsides. You can think about the outside as all the indeterminate forms, all the possible indeterminate forms. And inside is the computation that we carry out with the plug-in method. And every once in a while with your plug-in method, suppose you try something like, I don't know, 3 minus x all over x plus 2, and you tried the plug-in method. The plug-in method would take you outside. It would take you into infinity over infinity. And that's outside. It's violation. Whoa, can't do it. And so we're going to try to give special attention to see where did it come out from. How did it get there? We want to try find a mark this spot. Where did it get out? What was happening before then? Exactly what was happening before it went out. And so you can imagine a bunch of different buckets. And so for example, if you have 3 minus x, let me do this in red. In permanent red. If you have 3 minus x all over x plus 2, and you're doing the limit as x is going towards infinity, you're going to try the plug-in method, and it's quickly going to get out into negative infinity over infinity. That's outsides. That's out of boundaries. We can't do it. So then you have to go back, and the engineer's method will take you to exactly the bucket that it went out on. Using the engineer's method, you'll get that this is a -1. It's in the -1 bucket. And so that spot right there becomes incredibly important. This is the spot -1. That's where this one got out of hand. Before it went into La La Land over here, into indeterminate forms, it was getting really close to -1. You'll try to do the table and you'll see. And so this is I think this is a good analogy to put everything together. When you're inside here, it's all good. When you do the plug-in method and you get outside here, you say, oh, I gotta take steps back and see where did it go outside, so what was happening before. And that's where the engineer method becomes powerful. And well, I hope it helps. Maybe you guys can put some comments here. Should we cut this from the video or not? I think it's good, but I'll wait to hear what you guys say. All right.